right, so Sally always going to give us a nice review, I'm sure, about superbubbles and energetics.
Can I close this door just to make the
Lighting
it? Right. Well, I really want to thank the organizers also for inviting me to this conference. It's a real privilege to be here, and I've really been enjoying my time. Today we're going to be turning to, what do I have to walk away from? Over the screen? Okay. Today we're going to be turning towards smaller scale phenomena, in particular superbubbles that are contained within the host galaxy. So we've been talking so far about galactic superwinds, and so these are much smaller phenomena that are due to star clusters, individual star clusters with O and B stars that are present. So I thought I would open by showing just this one image of the nearest OB association, the Orion OB1 with its superbubble. So you can see that there is an ionized shell over here. This is Barnard's Loop. This is the constellation of Orion. I'm sure we all recognize it. This is just one side of the superbubble. The superbubble itself is the Orion Arrhythmus superbubble, which extends way up in here, has a lot of X-ray emitting gas. And I'm just showing that because when we look too closely, things start looking pretty complicated. We have some B stars here. We have evidence that the star formation looks like it's been perhaps not totally concurrent. We have the O6.5 star here in the Trapezium Nebula, and maybe you can start looking at things that might be feedback from individual stars, stellar wind bubbles, and so forth. But basically, I'm just going to kind of remind you with that image that whatever simplifications we make from here on out are going to be just that, perhaps oversimplifications. Okay, so this is still talking about mechanical feedback, in this case from O and B stars. When we were looking at the galactic superwinds, we were also considering AGN feedback. We won't be doing that here for obvious reasons. But within galaxies, mechanical feedback is still very important. It is the source of the hot ionized medium, the shock-heated gas, which is the low-density component of the interstellar medium. We have the interstellar phase balance between the different phases of the ISM that is largely modulated by this mechanical feedback and the energy budget of these different components as well. The hot, low-density gas is very good at carrying and transporting newly synthesized metals that come from the massive stars and their supernovae. And as a result, that means that we're driving the galactic chemical evolution in these star-forming galaxies through mechanical feedback. This is also opening these channels between the stars and the interstellar medium, and so that's how we manage to transport the metals in hot gas. And it also becomes very interested in another problem, which is the escape of Lyman continuum radiation from the parent stars. So superbubbles, here is my favorite object perhaps of all time, N44 in the Large Magellanic Cloud. We see basically that it's a nebular object because it's very young. There's still O stars present to ionize the gas. And we also have very hot X-ray emission that you see in the blue here. And so that's characteristic of one of the three models that we have here, and that is the adiabatic bubble. So when we have an energy-conserving bubble that is producing shock-heated gas, then you have this X-ray emission, and we'll look at that in more detail in a second. There are also these two other models, the momentum-conserving shell and the adiabatic wind, which we've already heard about. So we can take a look at these in detail here. The adiabatic bubble was first described in an analytic by P. Kellner back in 1968, and very simply, you can just derive this from units analysis. It shows that the radius of the shell will grow as the input mechanical luminosity over the ambient density to the 1/5 power times time to the 3/5 power. And this is assuming that you have a constant input mechanical power, which is this L term over here. So in the case that you have stellar winds, it's fairly straightforward. That means that we can take the mass loss rate for the individual stars times the terminal velocity squared, times half, and parameterize it that way, just for the aggregate sum of all of the O and B stars that you have in your cluster. Once you start going to supernova-driven objects, then you have to start making this approximation that the supernovae are kind of all going off discretely in time, but that over a while starts to approximate a constant wind. At least that's the simplest geoid order way to So then you just have the number of supernovae times the supernova power divided by the time scale over which this occurs. And basically, once the supernovae start going off, they dominate the luminosity pretty much from the start. At least that is the standard way of parameterizing this. And that's because if you integrate the stellar wind power over the entire lifetime of the O star, then you get a power or an energy that is basically the same as the supernova power. So the idea is that supernovae basically produce a lot more energy per star. They produce a lot more energy once they actually start going off. Okay, so the schematic for the wind-driven bubble, as many of you already know, you've got your mechanical source in the center. It's driving a bow shock out into the interstellar medium, piling up shocked interstellar gas on the outside. And then you've also got a reverse shock that is pointed back toward the source here. So this here is the really expanding wind, the purple. You've got your reverse shock. This is where you symbolize your hot gas. And so this region here, which dominates the volume of the bubble, is basically filled with hot 10 to the 6 or 10 to the 7 K gas. And it's the pressure from that gas that is driving the bubble growth outward, and hence we sometimes call these pressure-driven bubbles. So this is shocked wind material. You also have shocked wind material lining the inside here, and those two, this is separated from the interstellar gas by a contact discontinuity that is in the middle of this thin shell. And the thin shell is generally parameterized to be radiative, and that's why it's thin. So the pressure can also be parameterized analytically, and it decreases as time to the -4/5 power in this model. It's been simulated by many people, including some of you that are here over the many years, and this is what we often call just the standard adiabatic model for interstellar bubble. So I wanted to show you this rather intriguing data set. This is from Wachter et al., 2010. And what we're seeing here is a whole bunch, and she actually has about 50 of these objects. This is just a few examples, that are observed in 24 microns. So these are presumably dust-emitting objects, but they are very small. These are only a couple parsecs or so in size. And they are perfectly spherical, and these are seen around generally evolved massive stars. We see Wolf-Rayet, for example, the E stars. She also finds a lot around E stars. So nobody seems to have followed this up from a sort of adiabatic bubble model standpoint. And I think this strongly suggests to me that what we're looking at, because these are so tiny and these are massive stars, that is giving you the boundary of the termination shock, the reverse shock right here near the star. So this might offer a very nice opportunity for really testing the adiabatic model just on an individual star basis. To my knowledge, nobody seems to be following that up. So just throw that out there in case anybody is interested. Okay, so we also have the momentum conserving shell, and actually Norm had made a distinction between momentum conserving and momentum driven. I guess technically these would be momentum driven shells. You've got the wind that is still producing momentum. What you've got in this scenario is, let's go back to the adiabatic, if you had this hot shocked wind region had radiated away all its energy somehow, then it would collapse. And so then you would just be left with the wind basically pushing out directly against the interstellar medium. And so the evolution of that shell can be described as R going as time to the 1/2 power, derived first by Steigman, Strickmatter, and Williams. And then that evolution is not that different from what you get for the adiabatic model, which evolves as time to the 3/5 power. So perhaps one diagnostic that might be nice to look at is the ratio of the radius to the expansion velocity as a function of time. So for the momentum conserving evolution, it goes as time to the 1/2. For the adiabatic shell, it goes as time to the 4/5. So that ratio will actually grow faster for the adiabatic model. And then, as we've already seen, the adiabatic wind model of Chevalier and Clegg is basically the free and just expanding in a steady state. And that's a CC85 model. This is the plot from that paper. You have the sonic point right here as a function of radius on the x-axis, and so you can just model what the radial dependence of the velocity, the density, and the pressure is for such a steady state min. And again, this has been simulated many times. We've already seen some very nice simulations of this at this conference. Okay, so what is the actual power problem that I alluded to in the title? So for the most part, we're finding, punchline, that these shells tend to look too small for what you find the input power or input luminosity of these objects should be. Here I'm going to just show you one example of many different papers that have found this. This is actually from my thesis back in the previous century. What we're seeing here are models for 4 different objects. These are all superbubbles from OB associations where we were able to determine the stellar population very precisely because we were able to see the exact stars, obtain their spectral types, estimate the ages, and so forth. And so what we have here is a function of time for each individual object, and there's 4 of them here. We're able to estimate what the input mechanical luminosity is, and that's the dashed line that you see here, given that observed stellar population. So these are not Starburst 99 models. These are actual models summing the input mechanical luminosity for the observed spectral types of the stars. So as time goes by, then the stars will expire and you'll get supernovae, so that's what these spikes are that you see there. And you can then model what the expected evolution for the radius of that superbubble should be, and what the input mechanical, what the expansion velocity is doing, and that's in the dotted line over here. So what is the observed superbubble radius and velocity? That's what the horizontal parameters are. So the solid line is the observed radius, and we also have a constraint on the time during which you can observe this object. So on the left, these 2 objects are ones that we think are pre-supernova. They do not show X-ray emission. They show very low sulfur 2H alpha, suggesting that those are basically very, very weak shocks or non-shocked objects. So that means that if we are to estimate when we observed it, it should be before the supernova explosion and before the Wolf-Rayet stage, because there are no Wolf-Rayet stars in either of these 2 objects. So that's why the length of this observed, this line denoting the observed radius has this particular span of ages. That's the allowed ages that you would have for this object. Now contrast that with objects on the right. These 2 objects we think are post-supernova because they're X-ray bright, meaning that potentially the supernova has impacted the shell wall and enhanced the X-ray emission. We also see high sulfur 2H alpha, again, evidence of shock excitation there. And that is actually very consistent with modeling that Krause et al. Had done in 2014 to model the X-ray emission from supernovae impacting the shell walls. So in that case, we are constraining the age of the objects to be after the first 1 or 2 supernovae. We can also constrain the ages based on the observed stellar population. And so that's why the observation window for these objects is much smaller than the objects on the left here. Okay, so now we want to see how well do the observations agree with the input mechanical luminosity. So the modeled radius, as I mentioned, is here. The modeled expansion velocities in the dotted line, and we can get the observed radius and the modeled radius to agree at the same time that we get the velocities to agree for the objects on the left here and here. And for the objects on the right, it's not too bad. We're sort of maybe within 25% of the observed radius here for the modeled radius. And then for the expansion velocities, these are much higher. And again, that's probably because the supernova impact to the shell wall had re-accelerated the shell. And again, a very similar phenomenon we're seeing by Krause and their simulations. So you're saying, well, what's the problem then? The problem is that for all 4 of these models, we had actually not taken the exact observed mechanical luminosity that we see for these objects, but we had reduced this factor by an order of magnitude. So the input mechanical power over the ambient density had been reduced by a factor of 10. If we had not done that, then the bubbles would basically be predicted to be much, much larger than what we actually observe. So that is one expression of this power problem, or energy crisis, as some people have called it. To make it fit. Yes, exactly. It was basically just an ad hoc parameter. Yes, and I will, so what are the possible solutions? And that's the next slide. Thank you, yes. I just also wanted to stress that we're not the only ones that have reported this. Many people have seen this in the literature.
Wait, Sally?
Yes.
You see these things at about 30 parsecs in size or so, and if you hadn't reduced the luminosity by a factor of 10, you would have expected them to be, what, like 300 parsecs?
Maybe not 300, but 60, 100, something, yeah, okay. Something that's way off the scale. So the question is, yes. Well, yes, so basically the rest of my talk is going to be why is this? And that is one answer, yes. So possible solutions. We have basically a plethora of possible solutions. It's not that this problem is so mysterious. The problem is going to be figuring out which of the possible solutions is actually the answer, or which combination of them. And you have already mentioned a couple of them. So the first one is that the input power could be overestimated. So Norm just mentioned mass loss rates in stars. So in objects that I just showed you, those were pretty young objects. They were, well, two of them had not even had a supernova. So what's going on with the input mechanical luminosity in that case? It turns out that the mass loss rates for stellar winds of massive stars are actually not very well understood or determined from an observational standpoint. Norm gave us a beautiful overview of the Castor-Abbott-Klein theory for the line-driven winds. So if you're trying to estimate what the mass loss rates are, you have to take that model and make an estimate for your density distribution in the wind. And you also have to be aware of what ion you're looking at, because you want to be looking at the correct ion and making an ionization correction factor, and all those kinds of problems, because these are basically non-LTE pins. So it gets a bit complex, and in the 80s and 90s, people had been using H-alpha, and they still do, to estimate what the mass loss rates are, and also free radio emission. So in the intervening years, people have been using other techniques to start looking at the mass loss rates for massive stars, in particular X-ray diagnostics, and also phosphorus-5, which is supposed to be a very nice diagnostic. Is P phosphorus? Yes, I think it is. Thank you. And phosphorus-5 is supposed to be one of the dominant ions, ionic species, for the temperatures of the stellar winds. And it was found, actually, by Fullerton et al., that they basically thought that these are off by up to a factor of 130 in the mass loss rate from phosphorus-5. So we basically don't really know. This problem has been around for at least 15 years now. People are generally coming to a consensus that the mass loss rates do seem to be overestimated. You remember that the mechanical power scales directly as m dot. So what may be going on from some of these earlier measurements is that you've got clumping in the winds. The winds may not be very uniform, and of course the clumps have higher emissivity, therefore leading you to overestimate the mass loss rates. When you go to lower metallicities, there's even been such a problem that people are starting to label this the weak wind problem, where in fact it seems that the observed winds now seem to have mass loss rates that may be even lower than what is predicted from the CAT theory. So we may be at a state where we may not even fully understand the winds as well as we thought that we did. And again, just to illustrate the kind of degree of this problem, people are even trying to use bow shocks of swept up bubbles to try to understand what the mass loss rates are instead of the other way around. Okay, so that's one issue with the mass loss rates in stars. What about the post-supernova objects? For supernova-driven superbubbles, there may also be some issues. In particular, cosmic ray acceleration may be an energy sink to the superbubbles. We've heard about the galactic wind community trying to drive galactic winds by cosmic ray acceleration. Well, the superbubble people have not, to my knowledge, really accounted for that possibility in the growth of the superbubbles. So that could also be a factor. And in fact, superbubbles are supposed to be more efficient at accelerating rays than individual supernova remnants. For one thing, you would have, in a pre-existing superbubble, you've already gotten a preheated medium, which means that you have a lot of hot particles, and so you already have particles that meet the threshold for acceleration into cosmic rays. In addition to that, you've got stronger MHD turbulence and magnetic fields within a superbubble environment, all factors which further enhance the acceleration probability. And then having multiple supernovae going on, and complex shock structures, which you often get and see in simulations, those are all, again, potentially environments for accelerating cosmic rays. So the degree to which this may be a factor of slowing down superbubble growth is not well understood. We do feel fairly confident that superbubbles are accelerating cosmic rays, and we look at the energy distribution of the cosmic rays and the isotope abundances. So far, they seem to be consistent with what people expect for cosmic ray acceleration. Indeed, it would be very hard to explain cosmic ray acceleration without superbubbles. So here is a beautiful observation of the Cygnus OB bubble. And so on the right-hand side, we see an infrared image, 8 microns, just to show you kind of where the bubble walls are. The OB association is in the middle there. And on the left-hand side, we see the 10 to 100 GeV gamma ray observations in Fermi, and that shows us where the cosmic rays are being accelerated. So we actually see this in action. The question is kind of what is the actual luminosity that this would correspond to. Okay, so that is the source problem. Now what about supposing we don't have a source problem, but in fact we're actually losing our energy? So bubbles, if you look at them more carefully, often don't look like perfect uniform shells, right? They actually look like they have holes and instabilities and whatnot. So it was suggested by Harper, Clark, and Murray that you might have holes such that you're actually losing a lot of stuff through some of these blowouts. Now I can kind of tell you the story about the last paper in my thesis, which I submitted in 1995, called Bursting Superbubbles in the Hot Ionized Medium, in which we basically suggested that maybe we could burst some superbubbles and have some of the energy escape and maybe explain some of the small radius. Unfortunately, this paper was rejected, and I guess you weren't. At that stage in my career, one can imagine this is a rather demoralizing thing, and I didn't know any better, and I thought I was wrong, and so I let that idea lapse. So I actually feel quite vindicated that some very smart people now think that this is a reasonable idea after all. Okay, so Harper, Clark, and Murray were looking at the Carina star-forming region, which has a superbubble as well. And what they did was compare the two models for the adiabatic bubble and the adiabatic wind, the Chevalier and Clegg model. So here is a function of radius. You can model what the X-ray luminosity should be for the bubble, the adiabatic bubble model here, and the pressure for the adiabatic bubble. And down here you get the same quantities, the X-ray luminosity and the pressure for the adiabatic wind model, the freely expanding steady-state wind. And so what they found was that in fact the observed X-ray luminosity and the observed pressure were exactly intermediate between these two models for this particular object. And therefore that seemed to suggest that in fact you could get something that basically looked like it was intermediate between these two models. So that all seems quite reasonable. Here are some models from Rogers and Picard's and simulations. These are density maps showing you how you might get that kind of clumpy distribution with channels. And they find that these channels actually get initiated very early on. What they have modeled is a molecular cloud, something like 10 to the 3 solar masses, and they put 3 O stars in the middle of it, and they just set it out, and you see the evolution for about 0.7 million years, 2.3, and 4 million years. And the channels pretty much get generated almost immediately. So you can see a lot of that mechanical power is basically going to be lost through these channels pretty early on. Nonetheless, you still get the growth of the bubble, or cavity as it would look more like in this simulation. A lot of it also depends on the initial distribution, what kind of clumping you started out with in this model. Of course, eventually you end up with your instabilities, Rayleigh-Taylor instabilities, while you're still accelerating, while you're still pushing your energy-driven bubble out into the dense cold gas. Once you're decelerating your shell, then you end up with Vishniac instabilities. And instabilities will be clumping things and therefore creating inverse clumps, which are holes. Here is the real Carina Nebula. This is a nebular image, and the OB association is somewhere in the middle here. Just to guide your eye, you can see kind of this big kind of ridge that's extending over there. You can see that this looks quite similar, actually, in some ways, to the simulation that we just saw. One can envision channels in this gas. This is just the X-ray emission. The soft X-ray is seen in the blue here. I think that's 0.5 to 2 keV in blue. And the extent of the X-rays is actually much larger than what you see in this image, because in fact, the imaging with Chandra was really only over the central region, not kind of in this wider region. Yeah.
So I should have asked before, but I mean, you identify this as a factor of 10. In terms of the phenomenology, is that factor of 10 universal for all of the superbubbles that showed this deficit? Or
yeah, so for
some systematic study that shows how the
I would say that it has not been systematically tested in terms of parameters like that. Yeah. I think at present this has become a more theory-driven field, I must say, because back in the 90s, there were kind of a lot of observations that were looking at that, and they were pretty simplistic. They were basically just looking at the standard adiabatic model, and there hasn't been all that much work, I would say, looking systematically at superbubbles and kind of looking at the supernova-driven ones versus the young ones and so forth. So I think that would be a very great thing for somebody to do, actually. Okay, so, yeah, again, I couldn't really say. Yeah, and 10 may not even be the right number, right? I just picked 10, that kind of worked for the objects that we were looking at. Other people have found different factors, but they're all pretty big. Yeah, it would be really good, I think, for people to just go back to the observations and look at more detail. I mean, one thing is that it's kind of a lot of work to try to figure out what the actual luminosity is for the objects and concerning the age, and I think that's one reason why it's been done more systematically. Okay, so in Carina, you do see the hot gas, and then zooming out, so here is the nebula now that we were just looking at, and here's that ridge, and you can actually see that it is sort of on one side of a large evacuated region. So again, this does seem consistent with a scenario where you could have something intermediate between a simple wind-driven bubble and a more freestanding wind that is blowing right out into this empty region. Yeah, so X-ray emission has been observed here. I'm not sure about this region because that would have to be surveyed. Well, Townsley's, I thought Townsley's survey was really only in the middle of this region. Yeah. Okay, and then back to N44 and the LMC. This is actually the object that inspired the rejected paper, but basically you see a very well-defined shell here with Chandra emission that you can see in blue, and we could clearly see, even before those images were taken with ROSAT, that there was leakage out here. With Chandra, we're seeing some more leakage over here. The same coming on the backside, I'm not sure, but you can clearly see that blowouts do happen. Okay, so Another possible solution, switching gears again. Could it be that these objects are in fact perhaps somewhat pressure confined, or even greatly pressure confined? So far we've only been considering, expansion into kind of a uniform interstellar medium, and that the ambient pressure is negligible. Well, it turns out that basically all sources that are interesting for pressure tend to scale as the star formation rate. That is the thermal pressure, the magnetic, the turbulent pressure, the cosmic ray pressure, and even gravity. So if you get to, forming a really massive cluster, that scales the star formation, and you'll even have gravitational pressure. So here are 6 objects, and Guillermo Garcia Segura and I decided to kind of just do something really simple, which was crank up the ambient pressure. So for these 6 objects arranged in that position on that figure, we have 6 models for the same objects arranged in exactly the same way. And this is just for the nominal interstellar pressure, P over K of 10 to the 4 kelvins per cubic centimeter. We're looking at the density as a function of radius, again, on the x-axis. So this is basically a radial profile of these objects. So you can see the classic structure here for the adiabatic bubble model. And then we see the shell over here. But in all of these objects, or most of them, we actually predict that the neutral shell is someplace quite a ways removed from the ionized shell in here, and that there actually should be this sort of ionized halo around most of these objects before you get to the neutral shell. Now, these are not super deep images, so one can't really rule out that that's the case, that isn't the case, but it's certainly not what you would expect from looking at this image. So what we did was we simply increased the ambient pressure by a factor of 10, so now we're at 10 to the 5. And these are the same objects, and the x-axis has been rescaled, but basically now you see that the H1 shell is hugging the H-alpha shell much more closely, and that these H-alpha shells are all well confined and thin. And these basically look exactly how you would expect them to look. Yeah. Well, the ambient pressure. So you would just have to invoke some pressure source for the ambient pressure. You could do that, or you could just say that, you have a very turbulent ambient environment for some reason, or you can just pick whatever favorite excuse you want to increase the ambient pressure.
The evolution of the bubble will be different, whether it's
Okay. Okay, right.
Not the pressure, I think, it's the density.
Okay. Okay, well, so what you're doing is something far more realistic. We were just doing, almost just an analytic solution. It's a one-dimensional calculation. Yes. Yes. Yeah. Sorry?
What's producing the
The star, the central star. Yeah. Yeah, so just very, very simple. Well, and actually I should say the stars, plural, that were observed. So yeah, I'm not suggesting that these models are realistic explanations for these particular superbubbles. Yes, they are based on real objects. I think this is simply to illustrate the principle that pressure confinement could be a factor. Okay, and so taking this idea to an extreme, we have a model for an object in M82. This is generated by Tenorio Tagle and collaborators in 2007, where they suggested that this object was in extreme pressure confinement. This is a superstar cluster in an extreme environment, and they argued that this region could be very strongly pressure confined for all of the reasons suggested. And this is generating a very complex kind of cartoon here. So the green regions are regions of higher density, which you would therefore expect to observe in ionized gas. The black line here is the stellar cluster radius. And the interior of the shell, the hot bubble model, is actually the region between the reverse shot here and the outer shell. So that is now squished to this white zone over here. And what they also find in such a model is that most of the gas, actually, from the wind of the superstar cluster is essentially being stalled at a radius that's comparable to that of the star cluster itself. So most of the gas is not even being able to be expelled out from the cluster. And so this is an example of something where you had an extreme pressure confinement scenario. Now, when you have so much material that's still up in here, then you're really pumping up your density as well. And in that case, then you would therefore also be enhancing cooling. So that takes us to cooling as a possible solution. If you're cooling your hot interior for your bubble, then you're going to be losing that energy. It will no longer be adiabatic, and certainly not fully adiabatic. And we've already talked about several of these factors at various times during this week. Metallicity is kind of one of the first things one thinks about as mattering with respect to cooling. This is just a little plot that Sergei Sulich and I made at some point showing the evolution as a function of time for the X-ray luminosity of some canonical object. So this is at a very, very low metallicity of 5% solar. And then once a supernova goes off, if you take the supernova yield for that particular object and then allow it to cool, with the new metallicity, you find that the X-ray luminosity can go up by almost a factor of 10. Now, mind you, that is for an extremely low metallicity object, but that, again, just demonstrates the principle. Then we have mass loading. We've talked several times about mass loading this week. We can actually see strong evidence for mass loading. Here is a superbubble, once again, N44, in a paper by my former graduate student, Dan Jascott. These are the Chandra observations of this object, and you can see strong limb brightening here and the soft X-rays that you see in red, and very nicely consistent with mass loading at the shell wall. We also see somewhat hotter X-ray emission here in green, and that's the putative location of where the supernova might have impacted the shell wall in that object. And again, Krause et al. have modeled this and looked at another object which also looked strongly consistent with mass loading at the shell wall. And then we've also talked about clumping and instabilities once again. Krause et al. And Sharma et al. Have done some beautiful simulations that show that in fact what ends up happening is that these clumps and instabilities end up cooling down the individual bubbles and supernova remnants before they are actually able to combine into a uniform wind. I'm showing here some images from Yadav et al. Where we can see this visually. This is the density distribution on the left and the pressure distribution on the right. And you can see that you've got basically these discrete sources here, but that essentially the individual bubbles end up cooling so quickly that they can't really launch into a unified superwind. So that could indeed be the kind of dominant solution. I mean, it looks very nice, looks very beautiful. What we have here in a paper by Sharma et al. Is how many supernovae you actually need before you're generating the Chevalier and Clegg model. So that's right here. This is the analytic Chevalier and Clegg standing superwind right here in black. This blue dashed line right here is a line that corresponds to about 100 supernovae going off in 2 parsecs. And so basically you're talking about having to have hundreds of supernovae going off before you end up with the steady state wind scenario. Okay, so to solve the power problem, we have basically at least 4 different methods that we can do that. So we've got an overestimate of the input mechanical luminosity. We can make the mechanical luminosity escape through the holes and blowouts. We can be pressure confined, or we can lose that energy through cooling. Let's take this now to an extreme in terms of the cooling. There may be a scenario where we can actually suppress the superwinds altogether from a superstar cluster. We can take this to what we call the catastrophic cooling regime. And that's, I mean, I didn't invent this term, of course. This was suggested by Sulich et al. Back in 2004, and more recently, simulations by some of you, in fact, have demonstrated that this is an idea that actually seems like it is quite relevant. So what we're seeing on this plot here is a parameter space for the cluster radius versus the cluster mass. And when you go to the lower right-hand corner of this parameter space, that is where the catastrophic cooling turns out to be significant. So, oops, for very small clusters, very compact clusters that are very massive. This line right here corresponds to a locus that describes the boundary between when you can actually get the winds to launch due to mechanical power, as we described earlier, and when they don't. So if you have larger, more extended clusters, etc., that's the kind of typical scenario. But if you have very compact clusters, then you get into this regime where the winds may fail to launch. And actually, the locus of this line is not well determined. What we have is a dependence on metallicity, star formation efficiency, heating efficiency for the shocks, and mass motive, and other factors. But basically, the principle again is what applies. If you have an object that is very compact but very, very massive, you're going to be far more likely to be in this regime where catastrophic cooling might actually take place. So the idea is that you're trapping your gas close to the cluster, it's not able to launch very far, and therefore the high densities cause the cooling to run away and you fail to launch your wind. So we think we have an object where we actually see this happening in some detail. So this is a nearby galaxy, NGC 2366, at a distance of only 3.4 megaparsecs, which is only about 4 times the distance of the Andromeda Galaxy. And we have a giant star-forming region here that's sort of like 30 Doradus. That object is called Markarian 71. It first came to our attention as an analog of the green pea galaxies. These are very compact starbursts at about redshift 0.2. They're unresolved, even with Hubble. And they are candidates for Lyman continuum emitters in the local universe. So that's how we first got interested in this. Here you can see an image where O3 is shown in green and O2 is shown in red. And basically you can see this wash of green showing you that it's unbounded by the low density, by the lower ionization species. So this suggests that you get high excitation all the way out to here and beyond, suggesting that it may be optically thin in the Lyman continuum. And it shows all kinds of other signatures that are just like the green peas in terms of being optically thin. So if we back off from this a little bit, the blue here that you see is the neutral hydrogen column density. And you can see a gap in here. So it's just like a classical chimney. The white contours show you the X-ray emission from this object as observed by XMM. So we see signatures of classical mechanical feedback. And oops, what have I done? Okay. If we zoom into this object, we can see that there are 2 superstar clusters, B and A. B is 10 times less massive and luminous than A, but we think that the mechanical feedback that we're seeing from the X-ray emission and so forth looks like it's associated with B, right? This is clearly evacuated. You can see the shell walls are nice and smooth as though they've been pushed apart by pressure from a hot superbubble. So we suspect that this is the source of the mechanical feedback. And A, on the other hand, looks a lot messier, still has a lot of dense gas. You can just see a knot, which is where the superstar cluster is located in there, and shows signatures of radiative feedback like elephant trunks and so forth. So A looks a lot younger. Knot B has classical Wolf-Rayet stars, dating it at an age of about 3 to 5 million years. It's a little bit more extended. It even has an LBV star associated with it. Knot A, on the other hand, is buried within this compact H2 region. In fact, it's just like an ultra-compact H2 region. No stellar features have been detected yet from Knot A. I'm really, really going to try hard to get Hubble time to go deep in the UV to see if we can find the stellar photospheres on Knot A so we can see what the stellar population is. But basically, this is an extremely young object, certainly less than 3 million years, maybe even less than 1 million years. And it is much more compact, about 1.5 parsecs in radius. Yet this is the source of all the ionizing radiation that we saw from the H2 region, because it's 10 times more luminous. So, zooming in on knot A, we were able to obtain CO 2-to-1 observations. Those are shown in black. The red shows you the CO continuum. This was obtained with NOEMA interferometer. And if we look more closely, the line profile of the CO is split into two components of about 11 kilometers per second separation. Those two components separate on the sky. We see a red shifted blob here and a blue shifted blob here. The colored in the background is the continuum emission once again. So you can see it's on either side of the continuum blob. Those are separated by about 7 parsecs in projection. And the total mass in these clouds is similar to the total stellar mass in the cluster that we infer from its luminosity, implying an extremely high star formation efficiency, which is very similar to a couple other objects that have been reported like that in the literature. So we have the parameters for this object. We know the kinematics, we know the masses of this object, and so we can model this. So if we do a model for the momentum-driven evolution versus the energy-driven evolution, we find that it matches exactly for momentum conserving. So the predicted mechanical luminosity from the cluster is 5 times 10 to the 38 ergs per second, which is exactly what you would predict for a superstar cluster of that mass, 10 to the 5 solar masses. On the other hand, the energy conserving model is off by 1 to 2 orders of magnitude. So here we see a scenario where it's perfectly matching the momentum-driven model. We therefore have no superwind, no energy-driven superwind, and we essentially have, therefore, a suppressed superwind scenario in this object. That is, if the kinematics that you saw here correspond to outflow. That's in the observed molecular gas. Looking at the nebular kinematics, there are archived Gemini observations, and these are side by side, so they're on the same scale. This object right here, I shouldn't say object, this is the ionized gas that's kind of right over here on top of the blob is expanding at only 10 kilometers per second. So there again, that's very, very low. So you don't see a superwind in the nebular gas either. This object is truly remarkable because you can actually see what's going on here, as opposed to a couple other, yeah? Okay, this is not A, that's not A there, not B, it's over here. This is an image in the kinematics of H alpha, this is an image in the kinematics of H beta. Sorry. Well, these are archived Gemini GMOS data, and that's what it gave. But, you know, H alpha and H beta should have pretty much the same kinematics. Okay, so it turns out this is not the only object where suppressed superwinds have been discovered.
Just a question for the last one. What's the argument for the age of not going down if you say this is a supercluster, this is a superwind? So then you can't say this is an embedded cluster, therefore it must have less.
Okay, so there's no superwind present, so we don't really know what the age is based on the size of the object. Yes. 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 Good point. Okay. So M82 has also been suggested to have a superstar cluster, object A1. This was the one that actually inspired the Tenorio Tagle et al. Paper on the massively pressure-confined object. And that's because this A1 cluster is so tiny. It has, I believe, a diameter of about 4 parsecs or something like that. So again, we're talking about very similar objects in a tiny ultra-compact H2 region. These two objects appear to be similar. The same group has now published their report suggesting these are also objects where suppressed superwinds may exist. And so in fact, there are a few more objects in the literature that seem to be following this kind of behavior. And then finally, I just want to also point out, this is back going to the superwind scenario, but for the green P galaxies, which, as I mentioned, are unresolved, very compact objects, we may be seeing evidence of suppressed superwinds there as well. What we're looking at here are the wind velocities, the putative wind velocities obtained from high ionization species like carbon-4 and silicon-4 from cost observations. Blue shifted velocities as a function of a proxy on the x-axis for the Lyman continuum optical depth. So basically, for example, the low ionization absorption equivalent width for silicon-2, carbon-2, and so forth. If you go to larger equivalent widths, that means that you're going to higher optical depth. And the scenario has always been that, okay, if you're going to see Lyman continuum emission, you must have a very strong superwind blowing away your ISM so that you can actually see the clusters. Well, in that scenario, that means that if you are seeing the clusters, you are down at this end, and you must have a fast wind blowing away the ISM. So you would expect to see some kind of correlation that does this. Same thing over here, Lyman alpha peak separation is a proxy, again, for optical depth. When you have the peaks separated by large velocities, that means that you've got a lot of scattering, so you're optically thick here, optically thin here. So the same trend on both sides of this figure. So again, you see this sort of trend here, and you see this sort of trend there, but the most extreme objects are the ones at the top of the diagram here, where in fact these are somewhat optically thin, but they show no winds whatsoever, right? These are the ones with the weakest winds. And so instead, you might be seeing an inverse correlation there, suggesting that you might be looking at suppressed superwinds in the green P galaxies as well. Here we see the similar plot for the low ionization species, measuring the wind velocities now. Same thing on the x-axis as before. This is a little bit messier, but again, you can see this, a few extreme objects clustering in the upper left of the diagram. And the low ionization species are one step removed from the winds, since these are lower ionization species. So it's not a surprise that this looks a bit messier. So I'm just going to put that there as food for thought. If you have suppressed superwinds, that means you might be in a scenario now where you are dominated by radiation feedback instead of mechanical feedback. And so these have been, radiation feedback has been suggested to dominate at the very youngest stages in some extreme objects, which, if you have such a scenario, leads to the kind of more fundamental question of when, how, and whether superwinds get launched and under what circumstances. Okay, so I just had this one slide on radiation feedback. I'm out of time. But basically want to acknowledge that people are now starting to combine mechanical and radiation feedback in simulations, and that you could, in principle, start driving by radiation pressure and photon momentum some mechanical feedback from photons as well. Okay, so I will just leave it at that. Thank you very much.
More questions for this? So my very, very naive question is, particularly in the cases that you described with the suppressed superwinds, where does the power ultimately, the mechanical power ultimately end up? Why isn't it obvious in some way?
Yeah, so if in the scenario, well, basically the mechanical power has been converted, has been completely radiated away by the catastrophic cooling. And then maybe you may also have the kind of super pressure confinement as a factor that contributes to that as well.
So can't you see that?
Can't you see that?
Could be measured? At what way?
Right, yes. Well, this is something that I'm very, very interested in. In principle, let's see, I saw a paper, and I'm trying to remember who wrote it, but I saw a paper that suggested that it should be dominantly coming out in the nebular emission at 10 to the 4. But I think it's still early days for. There is a lot of dust in some of these systems.
It's just going to come out here in infrared.
That's right.
Yeah, already.
And in Markarian 71, you see strong thermal infrared emission. I had to see whether the volumetric luminosity is stronger in the infrared or the optical.
So I was curious if, in terms of the mass loading off of the shell picture for generating the pool, if you look at using the like 77 classical evaporation model, it's checking if the mass loss rates for that do enough cooling to explain this?
To actually slow down the bubbles.
Well, to load up the hot material so that it's denser, so that it cools faster.
Yeah, I mean, I think in principle that has been done by a variety of people. I mean, it's not something that we included in our original calculations.
It doesn't do it. It doesn't do it. You need more or less? A lot more gas.
Are these compact objects rare or common, or is there a census on what fraction of the star clusters are?
So how many of these star clusters fall into the super compact, supermassive category? So I think there are probably a lot of them, but to catch them at this very, very early stage where they have just formed is quite rare. Now, people have always been talking about the green pea galaxies as though they're exceedingly rare objects because they are just kind of like the very tiniest tip on the entire Sloan Digital Survey, where they have selected those particular objects in the most extreme kind of parameter space. But the fact that we're seeing an analog to the green peas that's only 4 megaparsecs away basically implies that these things are probably a lot more common than we think they are. And it's sort of like, okay, so we had Markarian 71, now we've had the 3 objects in M82. M82 is pretty close too. There's another one in NGC 5253. There's another one in, I think there's another galaxy. So they're starting to pop out more commonly now. So they may be more common than appreciated.
Just add to that, M82, first 4 or 5 star clusters is half the stars. So it's really common. About half the stars in those. It's very, very few handful of clusters, of which most of them come. So that's the star of its galaxy. But those stars form in persons. They're actually more of them.
So some of the examples which you've shown, for example,
Could you speak up a bit more?
yeah. So the one of the examples which you've shown, the Carina bubble. So there could be multiple events going on there. Like the age spread, if I remember, it's like more than 10 million or so. So is it possible to account for the multiple events, multiple bursts of star formation in such cases?
Yeah, in fact, multiple starbursts and kind of extended star formation are a complication that also has not really been looked at, I think, with respect to the superbubbles. Sometimes people have been modeling the 2-stage starburst, for example, and that may be something that is at play in terms of allowing the line of continuum radiation to escape from systems like Markarian 71, because in Markarian 71 you clearly saw the 2 blobs, right? You saw that there was not A and not B. You had the chimney, which was kind of classical feedback, and then you had this bizarre object that had just formed. 30 Doradus, similarly, you've got this old cluster, this old massive cluster that is 20 million years old, and then you've got 30 Dor, which is less than 3 million years. I think you've got 1 million years of this. Just the
What about you mentioned briefly the contribution of superbubbles to cosmic rays relative to supernova? Is there any even a vague sort of budgeting of that stuff?
You mean to where the cosmic rays themselves come
Right.
from?
So what
Yeah.
of cosmic rays can come from superbubbles?
As opposed to
supernovae?
supernovae, yeah. Well, certainly the people who model this are assuming the power law distribution for superbubbles. So I assume that they basically are doing sort of the individual supernovae versus everything as one continuous mass spectrum for clusters, in which case the contribution for the supernovae must be something like 20% or 25% or something like that. It depends on the power law. The luminosity function, yeah. I don't offhand know if that has been kind of looked at in more observationally.
There's sort of a difference between the evolution of individual supernovae and the supernovae.
Right.
The sizes, so in terms of what energy cosmic
Exactly.
rays, what energy state
Right.
accelerate the cosmic rays, all those things
Yeah.
depend on the
Indeed.
Right.
Yeah.
all that I know about this, and I don't know, I haven't studied this, it's not my area, but I believe that they are reasonably happy with the contribution from superbubbles, which is superbubbles just being parallel. But I would refer you to papers by Paradiso et al. I don't know whether Roland might have some ideas.
You mentioned a couple of superbubbles in the LMC, like 30 Doradus and N44. And I was just wondering, in a dwarf galaxy like that, I mean, what happens to the gas that you're driving out? Are you going to kick this material out of the galaxy on a galaxy scale wind, or is it going to stay bound?
Well, that's the million-dollar question, yeah. So some of the gas must be in the interstellar medium, because we certainly see that the hot interstellar medium in dwarf galaxies exists. And so a lot of that gas must come from there, because there's no other explanation for where that gas comes from. But some of it may also get ejected into the galactic medium, as we saw earlier this week. And that has always been a question for galactic chemical evolution, right? So can you maintain the low metallicities of some of these galaxies by ejecting the metals? And that would depend on the star formation history, the magnitude of the burst that you have, and so forth.
So you almost had no discussion of this, except at the end where it actually solved the problem. So are we, is it not important to consider dust in all the problems? Survive. I mean, I saw extinction in solid maps, so solid MSX. You know, when you said it was a conduit, to me it looked more like a Tesla. But that's.
But you see X-rays.
No, there was one area that there was no X-ray with that. But more to the point is survival of that region. Really dense
Right, so I think in terms of the photoionized gas, sure, dust is very important. I think when we're just kind of looking in terms of the expansion of the bubbles, the dust would be another component of the hot gas, another component of the interstellar medium into which the hot gas is expanding, or into which the mechanical power is expanding.
Yeah, I mean, the energetics, you're being likely that.
And energetics of the superbubble? How so? You mean that we need to account?
Include what's also being pushed.
Yeah, sure. Yes. So, like, I didn't mention molecular gas either. So, it all depends on what you assume the bubble is expanding into. So, yes, if you're expanding into the.
My question is, how much is known about the infrared emission and CO, molecular gas?
Okay, yeah, so then it depends sort of on the age of the object, because the younger objects do tend to be more associated with some molecular gas and some dust. We did a study of the PA emission from some superbubble objects in the 1990s, where you could see that in some of these younger objects, you did get some regions that were, those aren't quite as dense with the thermal dust emission. But yes, the environment gets complicated, and the more you take that into account, the more you can also end up with situations where if you have dense gas, it may be a denser environment and may be harder to push apart.
May not be powered by the star cluster itself. It just be the helium.
Well, I think Sylvain was suggesting that we needed to account for more phases of the interstellar medium, including the cold phases in the dust.
Including also the dust that may still be in the issue.
Okay.
Dust emission as well. Yeah.
So what?
A question.
So okay, so you're suggesting that the dust inside the superbubble would radiate away, would basically conductively accumulate some of the hot gas.
So I think the answer, Josh, you can see that it's 24 micron emission. Even a supernova, you see emission of gas mass. Right. Inside the supernova. Now, probably,
you see it there too.
You see these, you see 24 micron emission in the interior of those bubbles. There's plenty of stuff in there polluting the inside. Go look at Davina. There's always little nodules, some of which have stars, and some which don't.
and they're clearly evaporating material off their pink dust. So they're just spewing stuff into that hot gas.
As you start with that beautiful teaser, you showed this beautiful spherical shell at 24 micron. But you didn't come back to that with the other instruments that you.
Those were individual Wolverine stars.
Right.
Yeah, there was individual stars.
Single star.
I understand they were different, but in a sense,
Things like that. There's plenty more to be said about that, but it's 10:34. It's due to discussion.